We talked already about hedging with futures, hedging with bonds, which were static hedges, and also about replicating a particular option used in the Black-Scholes-Merton model. And now we want to talk about how to reduce risk of a portfolio, maybe of many options, many different assets. Right? So we are going to call it hedging portfolio sensitivities. The idea being that you want to just a second, let me find this. The idea being that you want to reduce the portfolio sensitivities to the movements of underlying factors. Let's see what exactly I mean by that. I'm going to think in terms of the Black-Scholes-Merton model, but the similar ideas would also be applicable in other models. Let's, as usual, denote by capital X the value of your portfolio. And at least in a model in which your portfolio, like in Black-Scholes model, your portfolio depends on the stock price, maybe time to maturity of different options in the portfolio, the underlying, well, that was the stock price, maybe on the volatility, maybe on the interest rate. And here's a slide just with the terminology and notation. These sensitivities are going to be measured as derivatives, mathematical derivatives of the portfolio with respect to these factors. And they have usually denoted by Greek letters, and so they're called Greeks, these option sensitivities in the option pricing language. And in the Black-Scholes-Merton model, these would be delta, which we have seen before, derivative with respect to the underlying, theta, which is the derivative with respect to time, gamma, second derivative with respect to the underlying, vega, derivative with respect to volatility, and rho, derivative with respect to the interest rate. Okay? The idea is, if you are worried about your portfolio changing very much, if the underlying, if one of these factors changes, then you want those sensitivities to be low. Now, it may be good for you if stock goes up, but not if it goes down, or if the interest rate goes up, but not if it goes down. But it may be also hard to control which direction your portfolio will change. So, I mean, it may be hard to change the sensitivity only in one direction, not in another direction. So you may want one way to keep the risk of your portfolio low relative to the movements of the underlying factors is to keep these sensitivities close to zero. Okay? Not too negative, not too positive. So that's one practical way of using the ideas from Black-Scholes-Merton theory for keeping the low the risk of your portfolio. All right, so let's see how that works. Oh, by the way, strictly speaking, in the Black-Scholes model, it doesn't really make sense to talk about the changes in sigma and changes in interest rate, because those parameters are supposed to be constant. But nevertheless, in reality, they are not constant. And you may worry about what maybe my Black-Scholes model with 1 sigma is more or less a good model now, but maybe sigma will change in the future, and it will be a different Black-Scholes model with a different sigma, and then you may want to see how sensitive up to the first order your portfolio is to the changes in sigma, for example. Okay, so this was just terminology and notation. Let's look at what the main idea is. The main idea is really the last equation, or approximate equation here, which says that we are going to approximate the change in portfolio, because really if I move x to the other side, then I get that delta x change in my portfolio is approximately this thing here. Okay, and this is what I'm concerned about, whether I'm going to make profits or losses, whether delta x is positive or negative. And this tells me that approximately the change in my portfolio is equal to delta of the portfolio times change in S plus theta of the portfolio, derivative with respect to time, times change in time, plus 1/2 gamma of the portfolio times change in S squared. Now, it might be better to write this as delta S everything squared, because that's what I mean. I mean squared change in the stock price. So where does this come from? It comes again from Taylor's expansion in calculus, which says if you have a function, and this is only applicable in the case when your portfolio is a function only of time and S, the underlying S. So if you have a function of t and S, then the value of that function in the future is value today plus first derivative with respect to S, delta S, first derivative with respect to time, delta time, change in time, 1/2 second derivative with respect to S, change in S, everything squared, plus 1/2 second derivative in time, delta t, everything squared, mixed derivative second with respect to time and S, change in S times change in time. Then we will have third derivative, fourth derivative, and so on. But if your model, if the reality is close to something like a Brownian motion model, then from what we were talking about in terms of quadratic variation, first variation, third variation of Brownian motion, we would guess that these higher order terms with delta t squared, the mixed terms, and then third derivatives and so on, are relatively small, and then we can forget about them. That's what's done here. We only take derivatives, first derivative with respect to time, first and second with respect to S. Okay? And that's why it's approximately equal, because we forget about the higher order terms. Well, okay, why do we take the second derivative with respect to time, to S, and not with respect to time? Well, we talked about that in terms of this mathematical notions of quadratic variation and so on. But economically, why we have gamma here, the second derivative, if you think about it, gamma as being the second derivative is the first derivative of the first derivative. So gamma is really the derivative of delta, right? So if you want, gamma is derivative with respect to S of delta, which means that you don't really want gamma to be too large, either negative or positive, because that would mean that delta is very sensitive to changes in the underlying, and delta is the number of shares you have to hold if you are replicating a payoff, like an option. So high gamma would mean very frequent trading. It would mean big changes, relatively large changes in delta, which means more frequent trading. High gamma on negative side or on a positive side would mean either large changes in either in reducing your delta or increasing your delta, selling or buying, more frequently than if your gamma is low. So in that sense, large gamma in absolute value, positive or negative, is not good if you have, say, high transaction costs when you trade. You don't want to trade too frequently. Right? You don't want your delta to change too much when the underlying changes. And that's the economic importance of gamma, which describes sensitivity of the number of shares you would have to hold, namely the delta. All right. So you want, for example, if you are very risk averse and you don't like risk, you would like delta x to be approximately 0. And you could do that by keeping, if you can, by having delta close to 0, theta close to 0, and gamma close to 0. Now, it may not be possible to keep them all close to 0, because after all we know that the Black-Scholes formula, or not formula, but the Black-Scholes equation says that Ct plus 1/2 sigma squared s squared CSS plus R SCS minus C0, right? But this gives you a relationship between Ct would be then theta of C, right? Plus 1/2 sigma squared s squared, this would be gamma, plus R S, this would be delta, minus C equal to 0. So this means if I fix theta and gamma, then I can compute what delta is. I don't have a freedom to compute, to change delta. Or if I fix delta and gamma, then I cannot change theta. Okay, so if I fix two of these, then I cannot change the third one. Okay? So it may not be possible to have a delta and theta and gamma all close to 0. Well, unless you put all the money, let's say, in cash in the bank account, risk-free bank account. But in general, it might be hard to reduce the risk completely. But it gives you the idea how this is used in practice, how controlling these mathematical derivatives of your portfolio with respect to different factors, controlling them also controls the risk of your portfolio. Okay. And there is, from the practical point of view, there is a lot of material out there that you could find, but here we are just learning about basic principles, and this is it. The Taylor expansion really is the main idea behind this, and that's the main principle, so I'm not going to talk too much about it, except to give some examples. But first, let's see what's next. From the previous slide, if you do make your delta equal to 0, okay, that's usually the first one you worry about if you want to reduce risk. And then your change in the portfolio would approximately be equal if your model is Brownian motion model and it's a good model, your change in portfolio would be approximately theta delta t plus 1/2 gamma delta s, everything squared. Right? This is, as we said before, really delta s squared. And you can see from here that at least as this second term is concerned, the second term will be positive if gamma is positive and will be negative if gamma is negative, because delta s squared is always positive. So in this sense, it's good to have, when you're trading options or whatever your portfolio has, it's good to have positive gamma, because the second term will be positive and your change in your value or portfolio value will have an extra positive term. Assuming that theta delta t doesn't change much, if you can change gamma to be positive, that's good for you. Approximately, doesn't have to be. It may. This is only, approximation, an approximation, and in the same sense, it's bad to have gamma negative. Okay? So already we talked about having too large positive or negative gamma. It may not be good for you because it means you have to trade frequently to reduce the risk. But also, if it is big, it's bigger. It's better that it's big on the positive side and not on the negative side from this approximation. Okay, so option traders talk about concavity and convexity of your portfolio. Convex functions are those that have a positive second derivative, gamma. So convex portfolio would be good and concave portfolio would be bad in this sense, in the sense of this approximation. All right. just to mention, if your portfolio also depends on other variables like sigma and R, volatility and interest rate, then you just do Taylor expansion of a function of 4 variables. So you have all the first derivatives, with respect to S, delta S, with respect to sigma, delta sigma, and so on. And then you have second derivatives, third derivatives, mixed derivatives. But again, you would cut it off here and, maybe here, maybe you would cut it off at some point and approximate by those terms that you leave. Okay, so that's the general principle.